Okay, I think we're good. So section 2.01, like I said, is rates of change and limits. The first thing we're going to investigate here a little bit is the rate of change side of things, and we're going to look at average speed versus instantaneous speed. So if you guys have had any physics in the past talking about motion and that sort of thing, you've probably dealt with this, even those that haven't have probably seen this in a science class at some point. So let's say that I've got, well, before I get to an example, let's just talk about this for a second. Average speed. What do you suppose that is when I'm talking about an average speed of something? What do you remember about that? Okay. So it's the change in distance over a change in time. A speed is really a ratio, right? Think about the units that we use for speed. Miles per hour, meters per second, that sort of thing, okay? It's a measure of distance or a change in a distance over a change in time. Okay, so let's say that I've got an equation for my distance that is 16t squared. Okay, so when objects are in free fall, this equation might look familiar, but when objects are in free fall, they tend to follow this kind of an equation, 16t squared. So we're going to use that, and let's say, and this is, so this is measuring the distance an object has fallen after t seconds. So then my question for you is, bless you, what is the average speed of an object during the first 2 seconds? Okay, so remember, the variables in this equation here, y is measuring the distance, and t is measuring the time. So if average speed is the change in the distance divided by the change in the time, how can I do this then? How can I answer that question? Okay, so plug in a 2 for t. So y equals 16 times 2 squared. And that's going to get me 16 times 4, which is 64. Okay, so by plugging in a 2 into this equation, remember the equation is measuring the distance an object has fallen after that many seconds. So after 2 seconds, the object has gone 64, I don't know, feet or whatever it is. I don't know what the measurement is for this one, or what the unit is for this one. But it's gone a distance of 64. Okay, so how can I use that then to calculate my average speed for this object? Divided by 2. Because the change in the distance is 64, the change in time would be 2, right? That's over that first 2 seconds. So, let's see if I got some room here. So the change in distance is 64. We know the change in time is 2. Now I want to caution you a little bit here because this particular equation, the distance and the time both start at 0, right? When t is 0, then the distance is 0, according to this equation, okay? What if the equation I had been using was like 16t squared plus 5? What would be the starting distance? 5. So then what would be the change? Exactly. Whatever you get when you plug in your number, then minus 5. So you got to be careful, okay? It's not just plug the number in and go. Remember, it's a change. So where are you starting, where are you ending? This is from 0 to 2, and 0 gets us 0, so we don't have to do that. But remember, you're doing a change each time. So in any event, our average speed here then, 64 divided by 2, so that's going to be 32. And let's say we were measuring this in feet, so this would be 32 feet per second is our average. All right, great. I think you guys are all okay with that. Now, what if I wasn't concerned about an average over a certain interval? Because we had to do this over an interval, right? From 0 to 2. What was the average speed that it was traveling in that interval? What if I wanted to know, okay, right exactly at 2 seconds, how fast is it going? I'm not concerned about an average. I'm not talking about an interval. I'm talking about at one instant in time, how quickly is that object moving? Okay? And that's going to require an instantaneous speed calculation. Okay, so instantaneous speed. Well, to calculate speed, I got to do this whole change in distance divided by change in time. Well, if I've got 1 instant in time, then I don't really have a change that I can measure for either one, right? So if it's 1 instant in time, what is the change in time technically? 0. Anybody see the problem with that? What happens when we're trying to calculate this change in distance over change in time then? Can't do it, right? You can't divide by 0. That's like one of the first big rules in math we talk about in high school. You can't divide by 0. So if we're doing an instantaneous, it seems like it's impossible. And in fact, for centuries, mathematicians thought it was impossible to calculate because of that fact. You got to divide by the change, and if there's no change, then you're dividing by 0, and you can't do it. But there's kind of a workaround that you can do. Let's say that my time, let's do so I'm going to do time t and t plus h. And this h is going to be some tiny increase in time. So if we make it like super duper small, like 0.0001 or something, okay? So yeah, technically it's still an average, but it's really, really close. So we can think, oh, it's got to be pretty close to the answer there then, okay? And there's a little bit of a workaround with that then. So if we've got these two, let's try that same thing again then. So let's see if we can answer the question, what is the instantaneous speed at t equals 2 seconds? Okay. So this whole change in distance over change in time, what is this going to look like now? Okay, well think about what we did. When we found the change in distance, basically we were finding the difference of the y values, right? So it's kind of like doing a slope, essentially. Change in the y over change in the x. Or instead of y, it could be f of and f of. So this is going to be f of t plus h minus f of t. That's the change in the distance. We have to take the t plus h and the t, plug them both in and find the difference. And then over t plus h minus t, if those are the two time values we're going to use. And in this case, because we want to find it right at 2 seconds, the t is going to be 2. So we're going to just take the t's and make them all 2's.
It's much excused, but I guess my mom didn't call yet, so
Okay.
she's going to change it.
All right. Okay, so that's where I'm at right now in doing this calculation. And the denominator, 2 plus h minus 2, that simplifies, right? What do we actually have in our denominator then? H. Okay. So f of 2 plus h minus f of 2 divided by h. Okay. So here's the thing. For h, for this thing to technically be instantaneous, what does h need to be if h is this little tiny increase after t? Right now we're kind of like approximating it because I said, make it like 0.001. It's like this teeny tiny little increase in t. But what do we really want h to be? 0, right? And again, right now, if I were to make h 0, that's a problem, right? Because then I'm dividing by 0, and I can't do that. Okay? So what we're going to do is, instead of doing this as directly and making h 0, which would give us something we can't get, we're going to think about it in terms of a limit. So we want h to move towards being 0 instead of jumping right there. So we're going to do this. The limit as h approaches 0 of this. And so we're going to go back to our equation, plug this stuff in, right? We still got to do this f of 2 plus h and this f of 2. Plug those back into that original equation, that y equals 16t squared, and kind of see where I'm at. Okay? So this then is going to get us the limit as h goes to 0. F of 2 plus h would be 16 times 2 plus h squared. And then f of 2, that we already did earlier, right? That was 64. So we're looking like that now. Okay, when you plug the 2 plus h in, you get 16, 2 plus h squared. When you plug in a 2, you get 64. So we're there. So now we can simplify this. We've got to square out that 2 plus h. FOIL that thing out. See what we get from that. So we end up with 16 times 4 plus 4h plus h squared minus 64 divided by h. And then if we do a little distributing there, get the limit as h goes to 0 of 64 plus 64h plus h squared minus 64 all divided by h. What? Oh, 16 h squared.